Hello everybody. Let's talk about some periodic trends. Alright, so we've already talked about ionization energy and size a little bit. We're going to review those real quickly. First of all, atomic radius. As you go across the period, they decrease in size from left to right. Why again? Because as you move to the right, numbers of protons in the nucleus, you increase the number of protons, but not the number of energy levels. So effectively, you're pulling the outermost energy level in closer. That is the reason. What about down a group? As you go down a group, the size of the atoms increase, and the reason for that is because there are more energy levels. 4s is larger than 3s, the 7s is bigger than a 6s, and it's just going to get bigger no matter what as you go down the group because of those additional energy levels. Like you just add layers to the atom. Here's a nice little graphic of that. You can see that even helium is smaller than hydrogen. As you go across the second period, it just gets smaller and smaller and smaller as you move to the right. And again, it's because we have 3 protons here, and here we have 10 protons pulling in the same energy levels. So all we have here is 2s and 2p. And that same energy level is being pulled in closer with more electrons, or more protons, sorry, with the neon. And it happens in every single case. And as you go down these groups, they get bigger and bigger, down every group, because there's more and more energy levels. So it's a nice little graphic to see what that looks like. What about ions? Well, ions follow the same exact rules and reasons for those. So, not really rules, but they have the same trends and the same reasons. First of all, you have some more verbiage to learn here. A cation, and a lot of people think it looks like cation, but it is a cation, is called, that's what a positive ion is called. And anytime a metal loses 1 or more electrons, they form a cation. Positive ion is called a cation. If you like cats, maybe an easy thing. Easier memory device for you because maybe you're positive about cats. I don't like cats, so that doesn't help me very much. But a cation is a positive ion. Once they lose electrons, they become a positive ion. The trend is exactly the same. Across the period, they get smaller. Down a group, they get larger. So cation is going to look exactly the same. So you can see that situation happening here. These are our cations. These metals that have lost electrons. Metals lose electrons. The non-metals over here, they gain electrons. And we'll talk about that in a bit. But these are losing electrons. So as you go down a group, they get bigger still. Same reasons, just because those outer energy levels are further away. As you go to the right, they get smaller and smaller. As you move to the right, for same reasons, the nucleus is pulling them tighter. Notice here how the size gets really big once you talk about the nonmetals. That's because they're gaining electrons, and there's more electrons out there that repel each other, and the electron cloud becomes bigger when the anions compared to the cations. So here they're losing electrons. Should make sense that the anions, these negative ions, which are called anions, are going to be bigger than the cations because they're gaining electrons. So there's another verbiage, more vocab for you that we will use a lot in the future. Cations and anions. Anions is a negative anion or a negative ion. A lot of people don't like onions, and it looks a lot like onion. So anion, once a nonmetal gains 1 or more electrons, they form anions. Trend is the same. So they kind of have separate trends, the cations and the anions, because they get smaller, but then the cations get smaller, but the anions are much larger. Then they get smaller as they move from left to right also. So same reasons, same trend, same reasons. Ionization energy. You worked on your packet a little bit, and again, this is just review. The amount of energy needed to remove the outermost electron, the ground state, in the gas phase. And when you pull that electron away, if it's held really closely and held tight by the nucleus, it's going to be tougher to do so. So the trends, as you go across the period, the ionization energy, or the amount of energy needed to make that happen, to pull that electron away, is going to increase because the nucleus is holding those electrons tighter. As you go down a group, it's going to decrease because that outermost electron is further and further away from the nucleus, so it's not held as tightly. So it's going to be easier to remove it. So here's just a nice little graph. If we look at period 2, lithium, beryllium, boron, carbon, nitrogen, oxygen, notice how there is a trend up. I know it does this little dip. The reason for that is, remember, beryllium is now filling the 2s. That's full, so that's fairly stable. So it's a little more difficult to pull the electron away. Same with nitrogen here. This is a half full 3p sublevel. That's a fairly stable situation. Remember how we talked about half full sublevels is pretty stable. So that's why we get this little blurb here. Otherwise, this will just keep going up and up and up. But there's a little blurb here. But overall, the trend is to increase as you go across periods. What about successive ionization? Well, this means after you remove the first electron, how much energy does it take to remove more and more? If I want to remove the second electron, what about the third? The big thing I want you to know about here is that a lot of times it's a big jump in energy. If we take a look at this graph, we can see how sodium has an ionization energy of 498 for the first electron. But the second electron is huge. It increases up to 4,560. You'll notice that every single time it goes up, no matter what we're talking about. As you pull one electron away, the other electrons are held closer, so any time you pull an electron away, it's going to take more energy the next time you pull another electron away, every single time. Okay, every number you look at. So this is sulfur, first electron, second electron, third electron, it just keeps going up. All of them will keep going up. But you have in this yellow shaded area is where it's a huge jump. So sodium 498, all of a sudden 4,560. Magnesium 736, 1445, all of a sudden 7,730. Huge jump. Why? Well, if you think about sodium, I'll just do a quick little Bohr diagram of sodium. It has 2 valence electrons, or 2 electrons in the first energy level. Then it has 8. Then it has 1. Well, the first ionization energy is to remove this one out here. Now it looks like neon, a noble gas. So the amount of energy needed to pull away an electron from a noble gas, now that we have our full energy levels out here, becomes very, very high. So why this big jump is occurring is because once you remove one electron, it now looks like neon, a noble gas. Same thing with magnesium here. Okay, magnesium has 2, 8, 2. All right, take 1 away, 736. That puts us down to having 1 on the outer shell. Take the second away, 1445. Well, look what it looks like now. It looks like neon. So we have a huge jump to now take another electron away. So notice how aluminum has 3 valence electrons. After the third, huge jump. So what I want you to understand is where the big jump occurs and why. Right? So anything in group 2, we expect to have numbers increasing, because they always do, but then a huge jump. Anything in group 5, like phosphorus here, I expect numbers, 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 but then after the 5th, now it looks like a noble gas, huge jump. So we want you to be able to identify, first of all, if I give you these numbers, what group something is in. Or if I just say, what about silicon, where would you expect a huge jump to occur? Well, it has 4 valence electrons, so 1, 2, 3, 4. After the 4th one, now it looks like a noble gas, huge jump. So that's successive ionization energies.
I've got to say, I love the trends. How about you?
2 more things to talk about. Electron affinity and electronegativity. Electron affinity is kind of the opposite of ionization energy. It is not the amount of energy needed to remove an electron. It's how much energy an atom would give off if you add an electron. So now we're forming a negative ion if we do that. So atoms that want electrons are going to give off a lot of energy. When energy is released, that means that the atom wants that electron. So who's going to want the electrons the most? Well, the ones that have the greater pull for electrons. So the right side of the periodic table, because as you move to the right, there's a greater pull. Except for the noble gases. The very right side are not going to want electrons at all. So the trend is very similar as before, and the reasons for it is very similar. So as you go across the period, it becomes more negative. That means that more energy is released. Release of energy means it wants the electron. Energy being released means that that atom likes to have that electron, and it's a stable situation, so it releases energy when it happens. So there's more attraction for the electrons as you move to the right, so that means that it's going to want that electron more. As you move down a group, the affinity, so affinity means want or like. So if I have an affinity for meatballs, that means I like meatballs. So I have a strong affinity for that food. In this case, we're talking about the electron affinity. So as you move to the right, there's more of a want or a desire for an electron, so there's going to be more energy released. As you go down a group, guess what? The electrons are further away from the nucleus because there's more energy levels, so there's less of an attraction or a want for more electrons. So as you go down the group, it's going to decrease, and less energy is going to be released. So because the electron is further from the nucleus. All right. The last trend we're going to talk about is electronegativity. Now, I'll be honest, this is the one that you're going to hear about a lot more in the future. You still need to know all the other trends, but the electronegativity is the one that's going to come up more and more pretty much every chapter from here on out. And the reason for that is because of this definition right here. It is the ability of an atom in a bond. After this chapter, we're going to be hitting bonding, covalent, ionic, how that works. So electronegativity is very important in that. So it's the ability of an atom in a bond to attract electrons. Remember, when things bond, it's because of the electrons. So these values are calculated or estimated. They're all based on fluorine. They are not actually measured. So fluorine has the highest electronegativity because it's in the top right. It's not a noble gas. It really wants electrons. It's got a tight pull for those electrons. And it's a smaller atom than any of the other halogens. So everything's based off of fluorine. So it's all compared to fluorine. The trend probably would make sense to you. So the want for the electrons, as we move across the period, again, it's going to increase because, same reason again, more protons, more nuclear charge, so we'll pull those electrons in closer, even when it's attracting them in a bond. As we go down a group, same thing as before. So that's why I talked about, if you understand the reason for the size of the atom changing, you'll understand pretty much all of these trends. As you go down the group, the want for electron again is less because the energy levels are more and the atom is further from the nucleus. So here are the trends. As you move across the right, they become greater. And as you go down, they become less, or as you go up, they become greater, however you want to look at that. But this is our big dog here for electronegativity, fluorine. And our little dog, if you want to look at it, would be francium. Big atom, electrons are very far from the nucleus, not that much desire for electron. Fluorine, big desire for electrons. These guys pretty much have zero electronegativity. Xenon happens to have some ability to attract electrons, but the rest of them do not even have a value for electronegativity. So in review, for some of the trends at least, we have the atomic number. We obviously know it will increase as you move to the right, but as you move to the right, remember we get smaller. Ionization energies increase because there's a greater pull. Metallic properties decrease. These are all metals over here, remember, and we have our non-metals. So these are the most metal-like, conducting electricity and such. These things are the most non-metal-like, so the properties of being a metal will decrease. Same type of thing over here. Atomic number increases, the size increases because we have more energy levels. Ionization energy decreases as you go down because the electrons are further away, easier to remove, and the metallic properties are going to decrease as you go down. So, or increase, I'm sorry, as you go down. And that should make sense over here. So we have non-metals going down to metals. So as you go down a group, they become more like metals all the time. So that is the rest of the trends. You will need to know these, the reasons for them all, and how they work.